Hello and welcome back. In today's video we're going to look at the Welly library for loading multiple LAS files into Python. In my previous video we looked at how to deal with this using a single file, or a single LAS file. But in the case where we have multiple LAS files, such as from a field or from a project, we then want to load them into Python in the most easiest and convenient way possible. And we can achieve that using the excellent Welly library that was developed by the Agile Geoscience group. You can find a link down in the description below to the GitHub repository where you can get this library. We are going to see how to explore the metadata of these well log files, and we will see where they are located using the Folium library, which is a mapping library, and we can interact with the wells and print information about the well itself, such as the well name. We will see how to plot gamma ray from multiple wells on the same plot. This will allow us to easily compare the different gamma rays between the wells. And finally, we will see how to check the data quality within these LAS files before exporting it to a PANDAS data frame. So let's get started. Now that we are in our JUPYTER notebook, the first step we're going to carry out is importing the libraries that we require. In this example, we will be calling upon the project module of the Welly library, PANDAS, and matplotlib.pyplot. We will import these by running the cell. Next, we need to load the data into our notebook. In the previous video, we focused on loading a single LAS file, but in this tutorial, we are going to focus on loading multiple LAS files at once. And to do this, we create a variable called wells, and then we assign it to project.from_las, and then we pass in the directory where the files are stored. In my case, I have stored them under Welly data. Then we need to pass in the asterisk followed by .las. And what this does is it tells the function to look in that directory for all files that have a .las extension. And when we run this cell, we can see at the bottom we have a number of iterations and the time taken for each file. Once complete, we can see that it has reached 4 iterations, and the rest of the message is warning us about some irregularly sampled depth data. This is not an issue, and the data will be interpolated. When looking at the raw values within the LAS files, it's just a case of an extra decimal point after about the 3rd or 4th decimal value. Now that the data has been loaded, we can start to view the contents simply by calling upon wells. And what we get back is a data table containing the UWI, or the unique well identifier, the number of logging measurements contained within each well, and the curve mnemonics that are available. With the wells object, we can access some of the key properties of each well, such as the UWIs, by calling upon wells.uwis and then running that cell. And what we get back is a list of the UWIs for each well within the wells object. We can also print out the representation of each well with a simple for loop. We start with for well in wells, colon, and then print well. And when we run this, we get the same information we had in the data table above, but it is now presented in a simple text format where we have the UWI, the number of curves, and the curve mnemonics. If we want more details about the well, we can call upon the individual well functions that we've seen in the previous video, such as the well name using wellheader.name, the latitude, and longitude from the well.location function. We can then print out these in a formatted string. Here I'm using /t to include a tab character between each variable. At the end, I have expand tabs with a value of 10, which will space the variables out nicely. So when we run this, we can see that we get back the well name, the latitude, and the longitude, all nicely formatted in columns. Perhaps a more useful output for this would actually be within a data frame containing these properties. And creating a data frame will allow us to easily access the information and work with the data like how we normally would. So rather than typing this section out, I will talk through what is happening. First, we create an empty dictionary called well_dict. We then loop through each well in wells and create a key using the wells UWI, and for the values, we will create another dictionary for our other key properties. We then create a data frame using pd.dataframe and appending .from_dict to it. In the brackets, we pass in the dictionary and set orient to index. And this means that the dictionary entries will be rows rather than columns. Next, we need to reset the index so that the UWI values are in a column rather than the index. And as we're applying this to an existing data frame, we need to set in place is equal to true. Finally, we will rename the newly created index column to UWI. We can run this cell and call upon wells underscore df. And what we get back is a nicely formatted table containing all of the relevant information for the well location, and this will be useful in the next step. Now that we have our data frame with the location data, let's make a map of where these wells are. And we can do this using a library called Folium, which is a great mapping package for Python. First, we need to import Folium and then set up our map. First, we need to create a variable, and we'll call this m. And then we assign it to Folium, and then .map with a capital M, followed by the brackets. And when we call upon m, we see that we generate the world map, which isn't very useful at the moment, but it shows that we can actually call this map. We now need to center the map on the location of the wells. Rather than picking one of the wells' coordinates from the data frame, we can calculate the mean latitude and the mean longitude of our wells and then center the map on those wells. And to do this, we create two new variables. First, we create mean underscore lat, and then we call upon wells underscore df, and then grab the latitude column. And at the end, what we do is we append .mean to get the mean value from that column. We can repeat that with longitude wells underscore df and call upon longitude. And once we have these, we can then pass them in to the location argument. And that takes us to a place known as the freeze front. But we're not quite sure where we are, so what we can do is we can set a zoom level, or a zoom start, to a value of 7, and what this does is it will take the map to a certain zoom level. So here we can see that we're off the east coast of England and the west coast of the Netherlands. The next step now involves adding markers to our map to indicate where our wells are. And to do this, we need to create a for loop where we iterate over the data frame using iter rows. And then we call upon folium dot marker, and then we pass in the well location that we've just created in the for loop, and we will pass in the latitude, and then we take the longitude, again the same way, well underscore location longitude. Next, we can add a pop-up so that we can click on each of the markers and identify which well is plotted where. And we can do that by putting in pop-up is equal to well location, square brackets, and we will grab the well name. We also need to wrap our location in square brackets so it keeps them together. And at the end, what we need to do is add underscore to, and then in brackets we pass in our map object. So there we have our well map with our 4 wells located off the northwestern coast of the Netherlands. And we can zoom in using the controls over here on the left, or by double clicking on the plot. And when we click on each of the wells, we can see the information about which well is where. And we can see that L06-06 is here, and then L06-07 is here. And we can add much more information into these pop-ups using HTML, but we will leave that for a later video. Another great feature of Welly is the plotting tools that it contains, and we can view the same curve from multiple wells on a single plot, even though they are not aligned on a specific depth value. We can use this to understand the data contents, extent, and the data character. We first create a figure object and axes by calling upon fig, axes is equal to plt.subplots. In the parameters, we can add the figure size and set the number of columns or subplots using the nCols argument. As we may have a large number of wells within our dataset, we can simply use the len function from Python to calculate the length of the wells object. We then need to loop through each well and assign it to an ax object. We will set up a gr variable and then assign it to the function get_curve. Inside the brackets, we pass in the curve name that we are wanting to get from the well, which in this case is gr. If it is the case that the gamma ray curve is missing, then it will skip and move on. If it is present, then we want to plot that data to the axis that the loop is at. And then we set the title as the well name, and then set up some matplotlib calls to tight_layout, which will manage the spacing between the subplots. When we run this cell, we get a useful plot back. We can see the depth on the y-axis, which is independent for each subplot. At the bottom of the plots we have the scale, and right away we can see that we have a few spikes in our data, such as this one here in L06-06, where the value is out to around 800 API. And this is a very high value outside the normal expected limits for this measurement. As we can see in the other subplots, we have values ranging between 0 and about 200 API. We can then repeat the above with the row B curve. And when we view this data, we see that there are large gaps in the data, which is a common occurrence within well log measurements. The more expensive or technical tools are often reserved for intervals of interest, such as the reservoir interval. And this is most likely the case for these two wells here on the right. Next, we will look at well log data quality, and the Welly library has some nice tools for gaining an overview of the data quality. To use this functionality, we need to import the quality module and the HTML module from ipython.display, as the results from Welly are contained within HTML tables. We then need to define the tests that we want to run using a dictionary object, and for each curve we want to check if there are no flat values, no gaps, and that the curve is not empty. We can also specify the tests for each of the logging curves. In this example, I'm checking both the gamma ray and the row B, or the bulk density curves, to make sure that the values are all positive between certain ranges and that the units are standard. We can run this and the dictionary is created. To run the tests, we need to call upon wells.curve_table_html, where we pass in the curve names and the test dictionary. To view the results, we need to call upon the HTML module that we imported from ipython.display, and within the brackets we pass in the data QC table. The table we get back shows the individual wells, the curves that have been selected, how much of the data is passing the tests, and then at the end we have the curves. And each curve in each well is presented with a colour indicator, where orange indicates that there are issues with the data and green indicates that the data is good. I don't find this table particularly useful and prefer a more detailed table for each well that again we saw in the previous video. We can view the finer details by creating a QC dictionary and then looping through each of the wells within the wells object. And for the key in the dictionary we will assign it the well name, and then we will assign the value to the QC table that we generate from the well module. And once that's done, we can then call upon HTML and then pass in QC_dict, and we can pass in the well name. So if I select L07-01 and run this cell, we then get back the table, or the QC table, for that particular well with all of the curves. And we can see where the curves have failed or passed the tests. In the case of gamma ray, we do have gaps, and same with the DT curve. In the row B curve, we have no gaps, but we do have a problem with the units. And we can repeat this with a different well. So if I go to well L06-06, we can see that we do have quite a lot of gaps in each of the measurements, and they're outside of the expected ranges that we set above. The final step we will look at is exporting the data to a PANDAS data frame. And PANDAS data frames are one of the common ways to work with data in Python and for machine learning. And it is as simple as creating a variable called df and assigning wells.df. And when we call upon the df object, we can see that we have a nice PANDAS data frame returned. And we can see in the index column, the UWI, as it is a multi-index data frame. So if we wanted to call upon a specific well within this data frame, we can call upon df.lock and then pass in the well name. So L06-06. And we can see the values for that particular well. Most of them are nans, but we do have some values within the gamma ray column. If you have enjoyed today's video, be sure to hit that like button down below, and if you want to see more content from this channel, be sure to click that subscribe button and hit that notification bell. If you want to see how to load a single LAS file using the Welly library, then this video up here may be of interest to you. Otherwise, if you want to see how to use the Log ASCII library to load in LAS files and work with them separately to Welly, then this video down here may be of interest to you. Thanks for watching, and bye for now.